Where are we?
I've taken off my coat. We're not on the iceberg anymore.
We've left planet Earth. Welcome to space.
We had to
Yes.
close all the breakout rooms.
And we're going to be talking today all about the influence of satellites on how we protect our planet. So thinking about looking down at the Earth, using the fleet of satellites that we have orbiting the Earth all the time, and how we use that data to think about our environment.
Sorry, I was distracted by a strange, ethereal alien voice. Yeah, actually, you know, the thing is, when you think about space normally, you tend to think about looking out, don't you? You know, satellites looking out into the cosmos, exploring other planets, landing on the moon, that kind of thing. But it's just as much about looking back on planet Earth. Earth observation, we call it, and the European Space Agency are one of the world leaders at that. And we're going to be talking a little bit about what that means and how important it is, because I don't think enough people know about it.
And some of the new missions that the European Space Agency are launching and developing at the moment. So we've got some real leading world experts in Earth observation to chat to in a second. Before we do that, if you have questions on the right-hand side of your page, you can drop those questions into the chat and we'll be asking those questions.
Difficult questions. I want difficult questions. Really, this is your chance if you're at school to think, OK, what can I ask some world experts about space and how it affects the planet?
Absolutely. Sorry. Social media, #POP24 if you want to follow us on social media. And as with all of the sessions, this one will be recorded. So if you want to check out the YouTube channel and see it later, in a few months' time when they've organised all of the feeds, then you can definitely do that.
You can hear the alien music again.
Yes, so...
right, who's our first guest?
Torsten. We have Torsten Fair from the EarthCARE mission. Torsten, are you there?
Earth calling Torsten. Earth calling Torsten.
Well, actually, he's done a little pre-record for us. Ah, there he is. He's done a little pre-record for us. Hi, Torsten, welcome. Perhaps he can't quite hear us right now.
Torsten, knock twice if you can hear us. Well, anyway, this is Torsten. We'll introduce him. We'll get the technical sorted out. That is Torsten, and he is working on a project called the EarthCARE mission, which looks at all kinds of things. It basically looks at clouds, and it looks at aerosols in the atmosphere from above to kind of monitor how much stuff is in the atmosphere. And all that stuff in the atmosphere are things potentially causing climate change. So we can measure them very, very, very precisely.
I think Torsten pre-recorded us a little clip, actually, talking a little bit about this mission. So perhaps we can play that clip.
Good morning. My name is Torsten, and I'm working for the European Space Agency in the Netherlands. And in the coming 10 minutes or so, I would like to show you how satellites help us protecting our planet. There is no clear beginning to what is called Earth observation from space. However, this picture of our little blue Earth rising in the endless space over the barren moon landscape has been a key moment in raising our awareness of the vulnerability of our planet and the need to protect it. It was taken by the US astronaut William Anders in 1969, almost 56 years ago, on board of the Apollo 8 mission circling the moon, and has supported the environmental movement in taking up speed in the 1970s. Later, Anders said, "We set out to explore the moon and instead discovered the Earth." And astronauts still have the best seat when it comes to observing the Earth. Like here, the view from the International Space Station traveling from Italy to India by day on the left side, or from India to China on the right. So why do we need satellites? Well, most importantly, satellites show us where we live. In Europe, in the UK, in England, or in Reading, where I'm at the moment. And they show us how we live, in cities or on the countryside, along the coast or in the mountains. From space, we have a unique view on the place that we are living in with great detail. Be it Glasgow in Scotland, or the beautiful hills in North Lancashire. Be it Manchester in winter, here covered in snow, or be it London. But they can also show us changes in the landscape. You might have expected that England is all green, but here much of England looks oddly brownish. This is a result of the summer heat wave in 2022 that led to widespread drought, changing the colors of the fields and meadows from green to brown. With satellites, we can monitor and see this from space, helping farmers by providing important information on their fields and crops. In fact, satellites can give us all sorts of information about our planet. We can have a close look at the Alps, giving us information on where fresh snow has fallen and where to best go skiing, but also information on where there is a high risk for avalanches. So better not going there and to stay on those ski slopes. We can also detect and monitor natural disasters, like volcanic eruptions shown here, but also wildfires, hurricanes, or earthquakes, helping emergency services to go where it is most needed, saving and protecting lives and property. But we can also see very remote landscapes and how they are transforming, like here, deep in the Saharan desert, from where sometimes thick dust clouds are transported all the way to Europe and the UK, turning our skies, but also our cars and windows sometimes, slightly yellowish. At the European Space Agency, we have a big fleet of satellites that are at this moment observing the Earth or that we are currently building. Our research satellites have the goal of advancing Earth science by helping answer fundamental scientific questions through observations of the Earth's key systems, like how are changing clouds for the future climate, or how many trees are there on our planet. With our Copernicus satellites, we are providing continuously information to support and improve the management of the environment, helping farmers with their fields, or providing information on the quality of the air we breathe. And our meteorological satellites provide 24/7 crucial information on the weather and climate of our planet. This data is fundamental to improve the weather forecast in the UK and around the world. But these satellites are not only taking beautiful images, they can also measure parts of the Earth's systems that are invisible to us. For example, wind, so the movement of the air made up of small molecules invisible to our eye. If we want to understand the atmosphere and improve our weather forecast, we need to know how the wind blows. This has been achieved by our Aeolus satellite. We call it the Wind Mission, using a powerful ultraviolet laser system. But no worries, there was no harm for us on Earth. With Aeolus, we were directly observing the movement of air molecules, water droplets, ice crystals, and small particles floating in the air called aerosols, all of them providing us information about the wind. Like here, as a wind curtain reaching from the surface to 20 kilometers over Europe, with red showing the wind speeds going from west to east and blue in the other direction. But also information on the transport of dust, smoke, and aerosols from forest fires or volcanic eruptions, like shown here for the Hunga Tonga Hunga Pai eruption in 2022. Or we can measure ever so little changes in the Earth's magnetic field, like here, where the magnetic field produced by the tides moving the salty ocean water is shown. The signal is only around a 100,000th of the full magnetic field that is steering our compasses. We can do this thanks to ESA's magnetic field mission SWARM, a constellation of 3 satellites dedicated to the Earth's magnetic field and electric field. Why is this important? Well, the Earth's magnetic field is protecting us from a stream of high-energy particles coming from the sun. No magnetic field, no life on Earth. But it also produces the mystical polar lights that we can see and that we did see earlier this year in the night skies. And it's also important for us to know these particles for the satellites themselves. They limit the space from where above the planet satellites can provide all the information about our Earth. As you've seen before, the space in the vicinity of our Earth is not empty, as the magnetic field is capturing fast charged particles that are coming from our sun and is doing so in giant rings around the planet called Van Allen belts. And while this is a protective shield keeping us safe on the Earth's surface from these energetic particles, this area is dangerous for satellites, as they can destroy sensitive electronic parts. This is why satellites stay outside these rings. We have 2 families of satellite orbits. Many satellites orbit the Earth relatively close to the surface, staying below the Van Allen belts, somewhere between 150 and 1,000 kilometers, or around 100 to 600 miles above us. This is ideal when we want to observe the planet in great detail, as the satellites are near to Earth. And most of the examples I show here are from these satellites. The other orbit family is called geostationary, located at 36,000 kilometers or 20,000 miles above the Earth and above the forbidden zone of the Van Allen belts. It is a very special point, as the satellite needs exactly 1 day to circle the Earth around the equator, and therefore are always looking at the same spot on our planet, ideal for weather observations. And this is exactly where we have, for example, the Meteosat third generation satellites observing Europe and Africa. This satellite gives us important information on the weather, for example, where thunderstorms and lightning are forming, how quickly the clouds are moving with the wind, or how humid the air around us is. All these individual observations combined allow us to provide images and data of the Earth that help us improve weather predictions. And all of this information goes into the weather forecasts you see daily on your favorite weather app or on the television programs. The quality of the air we breathe is key to our health, and satellites show us how clean or polluted the air is. Satellites like Sentinel-5 precursor shown here on the right can measure different polluting substances from space. This allows us to provide detailed maps of global and local air pollution, like here, in this case for nitrogen dioxide, which is produced in traffic and industry. And it is fairly easy to locate areas of high pollution. Maybe you can spot already the UK. But we can also observe greenhouse gases from space over time, as shown here for carbon dioxide or CO2. With satellites, we can measure the local and global concentrations in greenhouse gases, which is modulated by the seasonal cycle of the vegetation, taking up CO2 in spring and summer and releasing it in autumn and winter. However, CO2 in the atmosphere is ever increasing, and now it is at its highest level ever. And this is, of course, leading to increasing global temperatures, like here, showing that the temperature average for the complete planet in early November this year were at the highest we ever measured in any November since records began. To exactly understand the climate of our planet, we need to know much more on how the energy coming from the sun as light and the heat radiated from the Earth's surface is reflected back into space or absorbed by clouds and those little particles in the atmosphere called aerosols. In May, we have launched a satellite called EarthCARE, which is designed to exactly provide us this information that we never ever had before. Together with our Japanese colleagues, we called our satellite the White Dragon, because it's white. And the White Dragon can look vertically through clouds, like here, for thunderstorms over Italy and the thin clouds high in the atmosphere called cirrus over Sweden. When looking inside the clouds, like an X-ray image, we can see where there are water droplets, ice crystals, snow, or rain. And at the same time and place, identify what these little aerosols are made up of, be it desert dust, smoke from forest fires, sea salt coming from the ocean surface, or pollution from cars and factories. But they can also be just small ice crystals or water drops. With all the information, we can say which clouds are cooling or heating our planet and by how much, which is so important for us to better understand and predict the climate change. I hope I could show to you that with satellites we can observe many aspects of the Earth, helping us to improve our lives and to better understand the atmosphere, land, ocean, but also the snow and ice covered areas and even the core of Earth itself. And all this is important to protect our planet.
Torsten, thank you so much for that. We're going to have a live Q&A with Torsten in a little bit. Honestly, just looking at that, it's almost miraculous. There was a very famous writer called Arthur C. Clarke, and he said any suitably advanced technology is indistinguishable from magic. And I look at that, and I look at what is possible from what we can do in space in terms of protecting our planet and understanding our planet. And I just think people don't know about it enough. We go about our daily lives wondering about doing things up above our heads. All this stuff is going on. It is almost magical.
No, it's fantastic. It's wonderful. And actually, I'm really looking forward to asking all of your questions to Torsten at the end of this session. Some of them have come in already. Please keep those questions coming in, though. We really want to grill him on all things related to satellites.
And also, you can grill Susie as well, because you're a space scientist. So this is kind of your department. When Torsten was talking about the Northern Lights, I could feel you getting geared up, ready to jump in and say, no, it's not like that.
Well, I study the Northern Lights. So if you have Northern Lights questions, Aurora questions, you can send those in as well. I'd be happy to answer those for you today.
Fantastic. Right, we've got Tommaso now, also from the European Space Agency, who's going to be talking about a satellite called CryoSat, which kind of gives you a little clue about what it's about. Ice. It's about ice. So let's hand over to Tommaso.
Hello everyone, my name is Tommaso Parinello, and it's my pleasure this morning to speak to you from ESRIM, from the Visiting Center of ESRIM. ESRIM is one of the sites of the European Space Agency and is located in Frascati, very close to Rome. In this place, we welcome thousands of visitors every year to try to explain what ESA is. ESA is the European Space Agency. In ESA, we build and we launch satellites for different purposes. For example, to understand the beauty of the universe, we build satellites to visit our planets and the solar system, and even comets and asteroids. But not only this, in ESA we built satellites to try to understand how our planet works. These satellites are called Earth observations. And amongst of these satellites, there is one special one, which today I would like to focus on. It is called CryoSat. So why CryoSat is important? The north and the south poles of our planet are covered by permanent ice and snow, but you can find ice also in different parts of our planet. Think about Himalaya with big glaciers. Himalaya is the place, for example, where the tallest mountain on Earth, Everest, is placed. At the same time, scientists have discovered that our planet is warming up, and as a consequence of that, ice is melting. So the Arctic, which is the North Pole, and the Antarctic, which is the South Pole, which is, by the way, is the home of the polar bears and the penguins, are seeing these big changes. But not only there. Think about ice, which is on land and is melting. The ice goes into the water, and as a consequence, oceans are rising. So what is really affecting the North Pole, or the places where we have the ice, is not only there, it is really affecting all the people around our planet. Think as well that scientists are saying that because of global warming, our climate is changing. And also what is changing is our meteorology. For example, you can see extreme events coming more frequently. And here CryoSat plays an important role. CryoSat is able to measure constantly, has been doing this for almost 14 years now, the changes of ice and how our oceans are how the level of our oceans are increasing. And all this information is not only important for scientists, but is also important for policy decision makers to understand which will be our future and take the right step to protect our planet. Today, there will be other scientists and colleagues which explain in more in detail why this is happening, and also explain that we have other satellites that are monitoring our planet, trying to understand other key questions. I, this morning, will focus on CryoSat and try to explain you how it works and how this data is then transferred to ground and delivered to the scientists who do these incredible discoveries. The launch of CryoSat into space was a bit different. Instead of putting the satellite on the rocket on a tall tower, the satellite was put on the rocket, which was hidden in the underground silos. And because of this, the main engines could not ignite in the underground, so the complex gas pressurized system has to push up the rocket, and when off the ground, or after a few seconds, the main engine ignites. Also, the rings which were around the rocket, which were important to seal the whole rocket in silos, they fell off. Now let's see the real thing. the first stage of the rocket burned for about 2 minutes. After it finished burning, it separated from the rocket, and then the second stage ignited. It burned for about 4 minutes, and at a certain point it jetonized the fairings because they were needed anymore. The satellite was still inside this shield. After 4 minutes, it finished burning. It separated for the third stage, which did this quite uncommon maneuver. And once positioned the rocket and the satellite inside at the right exact position where we wanted, then it softly released the satellite. It took about 6 months to check the whole platform, the whole instrument, and how healthy they were. And after 6 months, the satellite was handed over to operations. Now we will move to the satellite, to a model of the satellite, and trying to explain you how it works. What we have here is a model of CryoSat. It's in scale 1/4, which means that the real satellite is 4 times bigger than what we see here. It's like a big car. Now, the shape of CryoSat resembles a little bit a dog kennel, with the roof with the solar panels. Nowadays, the size of satellites can come in different form, in different sizes, and thanks to the miniaturizations of materials, the 3D printing, and also digital technology, they can be very small as a school book. Now, the solar panels, one of the most important, I would say, systems for the satellite, because it basically generates energy. Satellite need, like your phones, for example, to work with it, need energy to work. And like your phone, there's batteries inside, and when the satellite is facing the sun, the solar panels are able to charge the battery like we do nowadays with our mobile phones. Now, just a fun fact, the solar panels which you probably have in your roof at home comes from space technology. So, beginning they were developed for spacecraft, for the ISS, for example, or satellite, but after this technology was transferred to everyday's life. This is not the only case. I would say that probably most of the things which are around us come from space technology. This is why important how to invest also in this, because the technology is then transferred to our lives. Another important element of a satellite is propulsion system. Sometimes satellites have to move into space to correct the orbit or have to rotate around one axis. This is done thanks to small thrusters which are around the satellite, and when commanded by the onboard computer, they function. They like springs, so when the spray comes out of one of these thrusters, the satellite moves in the opposite direction or it rotates. Well, CryoSat needs to know where it is, and in order to do this, it has 3 important cameras which we call star trackers. They're like the webcams or like the lens of your phone. What they do, they look at the stars, and based on the pattern, they know where the satellite is and gives this information to the satellite. Another important element which usually is used when the satellite is in trouble, when it goes what we say to safe mode, is the coarse Earth and Sun sensors. They're basically able to measure the light coming from Earth and the Sun, and based on the information it gathers, is sent to the computer. And with this information, the computer basically can try to fix the satellite's orientation if this is an issue. The satellite uses as well the Earth magnetic field for navigation, and based on the magnetic field it sends with sensors which are inside the satellite, this information again is sent to the board computer which uses it for navigation. CryoSat has to make very precise measurement of ice and how this is changing. And in order to do this, we need a precision of around 2 centimeters. Think of 2 centimeters with a satellite which is orbiting around 720 kilometers. Now, in order to do this, we have here a sensor which is called DORIS. It's a kind of antenna which sends basically signal to a global network around the world, and through complex geometrical calculations, we're able to know exactly where the satellite is with that kind of accuracy. Nowadays, systems like this are replaced by the GPS, which is basically the same technology again you have in your iPhone when you navigate and want to find a place. Well, the satellite needs to communicate with ground, and we have different antennas to do this. We have this antenna, which is called an S-band, and they're usually used to command the satellite from ground or the satellite uses that kind of antenna when he wants to communicate his status, what we call the housekeeping telemetry. But the most important data which needs to be sent to the ground is the data which comes from his instrument, which we'll talk in a second. And this is this big antenna here. But once all the data is collected, and the orbit of CryoSat is about 4 times a day orbiting basically our planet, this data, when we are in the visibility of what we call the ground stations, the data is then routed down. And now we come to the most important, I would say, system of the satellite, and this is instruments. But this, what you see here, the antenna of the instrument is called an altimeter. All the electronics are inside. Altimeter is an instrument which measures distances. To make an example, think about when you're trying to park a car. You may hear this beep beep sign, which is basically these sensors around the car, which is telling you how far objects are from the car, so that you can park without bumping into people or into these objects. Well, the altimeter works a little bit like this. These antennas send a signal to ground, and basically it calculates the time, the signal bounces from the ground and it comes back, and the computer on board measure the time delay. This gives an important information about how far, for example, ice or the ground is. Now imagine when the satellite goes around the same areas, it does exactly the same. If the ice is melting, it's clear that the distance from the satellite is becoming bigger. If the ice is thickened, then what happens is that the distance is becoming smaller. By looking at the difference between now and then, we are able to basically calculate what are the trends of the ice around our planet. CryoSat was launched more than 14 years ago, and it's still working very well and giving us all this important data to understand the climate change. Of course, the satellite cannot do everything on its own. Once the data is collected, this is downlinked to a ground station. The data is then checked by our ground teams, check the quality, process the data so that it can be used by the scientific community. When this is done, the scientific community uses this data to do the fantastic and marvelous, I would say, discoveries which we talked before. Now, this is all from me this morning. I hope you have enjoyed the video, and I'm looking forward to answer your question. Thank you.
That was amazing. I have learned a lot today.
Yeah, me too. Thank you so much. Torsten and Tommaso, that was wonderful. Thank you. We've got so many questions that have come through. I don't think I'm going to have time to ask them all.
Can I ask my question?
Okay.
Tommaso, I was just watching your beautiful presentation just then. And when CryoSat was launched, you showed a video of it being launched underground. And I was looking at that going, why on earth would you need to launch a rocket from underground into space?
Well, that was a kind of political decision because we were using the rockets which were used, which were planned to be using nuclear powers, and as part of them, the agreement between Reagan and Gorbachev at that time to reuse of military hardware for civil use, and this rocket was available, so we used that one.
Interesting, very
really
interesting.
Who knew? There you go, fantastic. Right, what have we got, Susan?
Yeah, we've got loads. The first question that quite a few people have been asking is how many satellites we launch every year with ESA, and I think that's because Torsten showed an amazing video of a clip of all of the satellites that are in orbit, and there seem like quite a lot. So how many does ESA launch a year in sort of Earth observation?
Yeah. Torsten, you want to go for that?
Yeah, well, I think this year we're launching in Earth observation around 6 satellites. This is a very particular good year for us, I have to say. So there are some years where we're launching a bit less. This year we're quite fortunate. We're launching quite a number of satellites. So we have been launching already quite a number of satellites. EarthCARE is one of our flagship missions, of course, from the European Space Agency that we have launched in May, as you have seen.
Just picking up on that. Is it every different space agencies, different countries launch different satellites? Are they doing the same thing, or do you kind of share satellites? Like if you've got one satellite that's looking at ice, can other countries, other space agencies use that data? How does it work?
Well, I would say it could be that different nations are launching different satellites, and this is because we need different measurements to complement what we already have to try to have a global picture of what's going on Earth. But sometimes we need satellites to more or less do the same thing, also as a backup, but also to try and what we say calibrate and get the truth, the measurement from different views from distant satellites, and that reinforces our knowledge about the planet.
Brilliant. So we've got a couple of questions. I think I'm going to direct them to you, Torsten, and we're going to pick EarthCARE as the example. Questions like, how much did it cost to build and how long did it take?
Oh, let's start with the first one. So EarthCARE was a particular complex mission, and you can already see Tommaso smiling there. It took us overall roughly 20 years to develop it. And if we start from the very beginning, the scientists themselves, they had the first ideas, say, in the late 80s.
Wow.
So it's basically since, I think I have a colleague who has written a first report in 91 or so. So it's since a long time. Usually we don't take that long for satellites. So roughly it takes 10 years. And EarthCARE was around 650 million for us, euros that is. And we have a cooperation with our Japanese colleagues from JAXA. And with them together, it is around, say, 800 million euros. So it is a pretty good investment, but it's one that we really need in order to better understand how the climate is working, how clouds are working. These are still the biggest uncertainties that we have in the Earth system to understand climate. So this is why we were so urgently having this mission being implemented.
That's fascinating. I guess for you, Tommaso, then, kind of building on that, if it takes 10 years or 20 years to do this, has science moved on in that time and has technology moved on? And would you launch the same thing, you know,
That's what I was
today?
thinking. Like, if you're going to launch your iPhone up into space and you launched it in 2007, it's going to be a very old bit of technology by now.
How does that work, Tommaso?
That is true. In a certain extent, when you start building a satellite, you have to stick to the technology of that time. But throughout the development of the satellite, I will say there are things which can change, but at a certain point, you have to also to freeze, I will say, the development. Otherwise, it would be difficult then to, you know, even for cost-wise, would be difficult. But on the science side, it's a bit difficult. Actually, in those 20 years, we're continuing doing science. We can doing also Caval campaigns. I mean, the community is growing as the satellite is developed. And at the end, we reach from the scientific, on the scientific community, we reach a kind of a knowledge which is ready to pick up what the satellite will measure.
Yeah, it's a continually evolving science and technology. It's interesting. So, Torsten, can you tell me, what is the average lifespan of a satellite?
It very much depends on where we have the satellite. So, for example, we talked about EarthCARE, and EarthCARE is flying relatively low at 400 kilometers. This means that these little air molecules that are still there are kind of slowing us down all the time, and we have to basically have to get on the gas pedal in order to work against this. So this is why EarthCARE might only be there for 3-4 years. We're all hoping that we will get much more, but it also depends on the sun, how this is working out. Other satellites which are in higher orbits, say 800 kilometers, they can stay for much longer, 5 years, 7 years. We have even satellites that are there for 20 years and they're still working, although we only planned for them for possibly maybe 5 years. So it really depends on where you put the satellite.
Interesting. One for you, Tommaso, about how we make sure that when we launch satellites, we don't damage the environment. And another question actually kind of linked to this, what happens at the end of their life? How do we make sure that we're not doing damage with our discarded satellites at the end of their lives?
Well, the answer to the first question is, of course, that there is a small impact, and what ESA's very, I will say, committed to try to minimize this, using different materials, using different fuels as well. Try to be sustainable as we launch them. The second question is, well, it depends where the satellite is. Now, for example, ESA is also committed to make sure that what we launch comes back safely on Earth, and with the zero debris, as we say, program. Some of the satellites would not be able to come down because, like CryoSat, is so it doesn't have the potentialities. But the satellites which are now launched into space, actually, they have to return according to some, I would say, European policies. Just one example, ALOS, which was launched 5 years ago. We entered last year, and we make sure that it re-enters safely over the ocean.
One thing, one of you, I forget who it was, mentioned, you talked about satellites getting smaller and cheaper to launch. And I'm just thinking about the future. If we kind of project 10 years ahead, are we going to see an exponential increase in satellites being launched into low Earth orbit? And what's that going to do with our measurements for understanding the climate?
Well, the business is there, I would say, and also the science is there. I think the number of satellites, the small satellites which are going to be launched in the future, it's going to be like exponential. And also not only for Earth observation, but we see now Starlink, for example, for communication. And so this is what we expect.
It's a very exciting time for us.
So smaller satellites, smaller means cheaper as well, because obviously getting things into space. And in terms of the kind of data that we're going to be getting back, what's it going to look like? If the technology that's up in space now is already a few years old, if we imagine the next sort of batch of technology, how accurate is that data going to be? Like, would we be able to look at the climate, look at the planet in real time, as it were?
Who knows? That's the beauty of science. That's the beauty of the future, maybe.
And I mean, we're already doing this. We already look into parts in real time on our planet, and this is how we do our weather forecast, for example.
Yeah.
There will be a lot of data coming that we have to coordinate, and this data stream, we will also use new technologies like artificial intelligence, for example. So this is really an exciting time for us with all of these different data streams coming together and helping us to better understand climate, of course, but also the Earth system itself. There's still so many questions.
So,
I'm sorry.
I was going to just, we probably need to wrap up, but just sort of a last one. If I was year 5, I've got some questions here from year 5, people who are about 10. What would I be looking forward to? If I want to go and be a scientist one day in 10 years or 20 years, what's your hope that the Earth observation will look like on that timescale?
Go and work for ESA.
Go work for ESA, yeah.
Well, probably you have seen this slide from Thurston. We have so many programs, so many satellites ahead that we would like to launch. And as we say, we have more ideas than money, and that is it's okay. So I think we have a really nice future in Earth observation in the future. The problem is, of course, is to find the right resources to do that.
Yeah, it generally is that equation, isn't it? More ideas than money.
Yeah,
I think that's it's been absolutely fantastic talking to you. And the thing that I'm just amazed is generally people don't really understand what's going on in space. They look at maybe space things on the news and they might see big rockets being launched.
Yeah.
But actually it is so fundamental to life on Earth now. Just all civilizations now are built on what we do in space. It's incredibly important.
Yes. So thank you so much for joining us both. Thanks for giving up your time. We really appreciate it.
Yes.
Thanks for answering all of our questions. Just to wrap up the session, I just wanted to mention that there are resources. If you're interested in Earth observation, you can go to the ESA website. There's extra resources there for you if you're interested in learning a bit more about Earth observation.
Can I do a little plug? I do a podcast for the UK Space Agency, the Satellite Application Catapult. It's called In Orbit, and it is a podcast all about Earth observation. So if you're interested in this area, about what we're doing in space and how it affects life on Earth, not just climate, but Earth observation generally, then In Orbit is a good place to look at.
Fantastic. Right, so looking forwards, if you're interested in the next primary session, it's called Pop into the Forest. It starts at 10 o'clock until 10:40, and it's going to be coming from the Eden project, so that's going to be hugely exciting. Do go and join that one. If you scroll down to the bottom of your screen, you'll see the link that takes you there. We've also got Climate Detectives Kids and Twilight for Teachers towards the end of the day, so hang around for those. They're going to be fantastic. We
are jumping back into the iceberg.
Are jumping back into the iceberg. I'm going to find my big coat.
To ice.
And we're heading to talk all about ice and how to protect our ice. So do join us in just a few minutes.